Hello, everyone. Thanks for joining us today. I'm the host for today's webinar. My name is Charles Rice, and today we're going to be focused on importing simulation data into SimCenter Test Lab. And our presenter today is Raj. Raj, you want to introduce yourself?
Yeah. Hello, everybody. My name is Raj, and I'm in the SimCenter customer support team supporting our product SimCenter Test Lab.
Great. Thanks, Raj. Before we turn it over to Raj, I just wanted to highlight a few things. First, one with regard to webinars we've already presented. The first one in this series was FRF acquisition techniques. And the second was a little bit theory-based about block forces and frequency-based substructuring. But as I said, today we're going to be focused on importing simulation data into SimCenter Test Lab, just so you know where today's material kind of fits into the process. As stated already, we kind of have 4 steps in this VPA module, Virtual Prototype Assembly. And that's characterizing our sources, storing and exchanging data in our component library, virtually assembling our component, and predicting the noise and vibration results. And being able to import data from various sources is very important, whether we're talking about characterizing our sources. Maybe we have to derive our forces using matrix inversion, so we'll have a lot of FRFs, or maybe with regard to our receivers, a prototype that hasn't been built yet. We just have a CAE model, and being able to generate FRFs and work with those and apply forces is very important to the whole VPA process. And that's what Raj is going to help us to appreciate today, how easy it is to import simulation data and work with it within Test Lab for this VPA module. Well, Raj, let me make you the presenter, and we can turn it over to you.
Thank you, Charles, for that great introduction related to the VPA series and putting into context where this importing of the data, simulation data into SimCenter Test Lab comes into the picture. The main focus is going to be in this middle part of this flow of information in the context of VPA, the Virtual Prototype Assembly. And so today we'll be focusing on building these components that is part of this Virtual Prototype Assembly. And these components can be built from test data, like using physical testing, or from CAE data, like simulation data. And the simulation can be from 3D models or system simulation model from 1D. 3D meaning the finite element based analysis, and 1D meaning like the physics based analysis and such. And so we'll see how to bring this data into Test Lab to generate this component library, which will then be used for this virtual prototype assembly. So with that, let's look at the agenda. So first, we are going to look at simulation data, how simulation data can be brought into Test Lab, and what does it mean to bring into Test Lab. Then we are going to talk about SimCenter Test Lab 3D driver. That is something which you can install to get more flexibility into how you handle the CAE or simulation data. Then we have to provide overview of the virtual prototype assembly and how it is integrated with simulation. And finally, I'll wrap up with some final thoughts for this webinar. So with SimCenter, let's see how to bring in simulation data into Test Lab. Now, when we say data, the data can be different forms. Sometimes the data can in the form of raw time history, or also called the throughput data. So this is, for example, if you have some microphone signal, which has a unit of Pascal with x-axis as time. So we can see how it is changing as a function of time. This is throughput data. The data can also be in the form of frequency domain data, like an FRF, like a frequency response function, which is output over input. And in this case, if we see this frequency domain FRF, this has a unit of G over N. So that is acceleration over force. X-axis is frequency. So the frequency domain data can be FRF or spectrum, or even orders and levels, order cuts and levels, they can be there. Or the frequency domain data can be in the form of waterfalls. Waterfalls can be thought of as 3D data because they can be plotted in a 3-dimensional display. Here we see an x-axis is frequency, and this axis here is RPM, and this axis is amplitude of vibration. And so we can see how the spectrum is changing as a function of RPM, for example, how the amplitudes are changing. So it can be that type of data, or this data can be in the form of a geometry, like a 3D geometry you can have, and the mode shapes from modal analysis, you can have that data also. So this mode shape can also be brought into Test Lab. So the data can be in these formats, and they can be read into Test Lab. And we have seen that a lot of different softwares, they generate different types of file formats. And the common ones I'm going to show you now, but there is a huge list of data that can be brought into TestLab. That is because the flexibility TestLab offers in terms of reading the data. So the data can be in the form of Excel file, for example. You can bring in time history data, you can bring in frequency, and you can bring in waterfall data, or they can be like wave files where you can bring the time history data. And similarly, Nastran, ANSYS, Abacus, those files can also be read. Now, I'm going to show some examples more detail related to the Nastran data, but the same concept would apply to any of this data if they're already compatible or they're applicable. So for example, Nastran, there can be a .pch file, a punch file, or a .op2 file, or a .bdf file. A BDF file only has geometry information, so we can see that that can be read in TestLab. And the punch file, it can have frequency domain data or waterfall data, so we can read that also. And similarly, ANSYS RST file, it has a geometry and mode shapes, which we can read. And so you can see that a lot of different file formats are supported in the SimCenter TestLab. And what makes it great is that you don't need any additional license to read this data. So we can just browse to the data and we can read the information in that file. And when we browse to the data, we can see the corresponding icon related to that file format. For example, if it is a Nastran data, it will have this type of icon, and ANSYS is this. STL, stereolithographic, like that has geometry information that looks like this and such. So TestLab is able to read that information, and then we'll be able to access that in a very easy way. One thing we recommend is to install this SimCenter 3D driver, the TestLab SimCenter 3D driver. This gives more access to the information in the files, and that makes our life very easy when it comes to something like virtual prototype assembly. Okay, we will take a look at that in some examples. Let's take a look at how can this data be read in TestLab. So I have TestLab open here. The latest version yet, TestLab 2206.0001, service level 1 version. I have created a shortcut for this example data, and I can see this example data. I have different file formats, ANSYS ASAM file format, which is an excellent file format if you want to exchange data with other softwares, because you can not only bring time history, but also waterfall, order cuts, all that information can be there. So let's take a look at that ASAM file format. So I can simply browse to it and then be able to access the content in it. And for those familiar with the TestLab format, it looks exactly the way TestLab, the data is organized. So this is an ASAM file format, ATFX or BDF file that was created from another software. And we are just able to browse to it and look at the data. This is a waterfall data. I can just browse to it and plot the data in TestLab like this. And then if it is an order cut, I can look at those also. Or if it is throughput data, I can look at that data also. I can just plot it here. I think my x-axis was too wide. So this is about 10 seconds of data. So you can see that you can browse to the data and be able to access the data very easily. Even data in something like an Excel file, which can be throughput data like the time history data, or it can be like an auto power spectrum. So I can plot that also here. So this for example is auto power spectrum from a microphone, drivers right here. When you are reading data from Excel file, it just needs to have a certain header information. And in my slides, I'm going to show that. And if you just provide that header information, then we are able to read that data in TestLab. And once we read it, we can simply zoom into it or zoom into a specific area. Or if it is in Pascal, if I want to change the unit to something else like PSI, I can do that. Or if I want to show another unit like bar, TestLab automatically handles all the units because it knows the scaling factors associated with converting one from one unit to the other. So for example, if I plot this in the form of amplitude, and if we zoom in here, so let's say it is in bar, and if I change from bar unit to Pascal, right, you can see that the scaling has changed, the limits have changed, and that's because TestLab knows the conversion factor to go from bar to Pascal and vice versa. So that's the advantage with TestLab. One of the advantages, I should say, is how it will handle the unit. And that is one of the reasons why several of the simulation engineers, they like to use TestLab, because when somebody asks them to plot some data, and they may be showing in millimeter per second square, but if they ask them, hey, can you show me that same information in a meter per second square or some feet per second square, for example, right? So the conversion can be done very easily in test lab in the display itself without having to rerun the whole simulation itself. That is one unique advantage of test lab. So similarly, there are other file formats. So we can take a look at, for example, an STL file. An STL file is a stereolithographic file, and that has geometry information in it, and I can browse to it and I can show the geometry like this. So this is the geometry of F-16 aircraft, and we can see that we can bring that easily into test lab by reading that file. Typically, when we do something like a modal test, we will create what is called as a wireframe model with some limited number of locations. So let's see if I can plot that. Okay. We will take the data, but using this STL file, and I can basically superimpose the modal data that I'm collecting from the test onto that STL geometry in what is called as mode shape expansion, so that I can show the test data on a CAE geometry. And that can be very helpful in terms of visualization purpose. So that is another file format. And I want to show our support of this data from Nastran. So the Nastran data, when we browse to it, we can see the icon for it. It automatically appears there. And that tells me that this data is supported in test lab. And if I click on this Nastran example data, this file, it is actually a punch file, a PCH file. A PCH Nastran file is like an ASCII file that can be opened in Notepad. So here I have this file, and the same file that I have opened, I have browsed to it from test lab. And we can see that here in terms of the node names, it shows that in the form of body command 2510, where actually, if we look at the information in the punch file, it just has node number without including that description for body or anything like that. So that happens because we have this point mapping convention that whenever it sees the 2510 in the file name, then it will transform it to recognize it as body : 2510. We are going to look at that shortly. But I can browse to this file and then I can show it here in a display, let's say like this. And I'll say limits free. Then I can see it in the form of millimeter per second square over Newton. That's what it came in. But I can, if I want to show it in meter per second square, I can just go here and change it. Then it will apply the scaling, that is division by 1,000. It applied it here and put the correct limits here. And when I look at the data here in test lab, if I want to do some calculation, let's say if I want to find an RMS value over a certain frequency region, then I can say I'll put a double cursor X. I can move this cursor and I can do some calculations on it. And I say RMS, then it will tell me what is the RMS value for this curve within this frequency. And note that I just browsed to the file to access this information. I didn't even have to copy the data or convert the data into test lab format. I can just directly access it. And if I change it to dB format, it automatically changes the unit and then shows me the RMS value in this way. So you can see how easy it is to browse to the data, plot it, and then be able to manipulate the data live when we are looking at the data. In fact, one of the other advantages is that we can create what is called as an active picture. If we copy the data as an active picture and plot it into, let's say, like a PowerPoint file, then I can interactively access the picture as if I am in test lab. So I'm now inside PowerPoint outside of test lab. So I'm not using a license of test lab. And if somebody says, hey, I want this color in blue, I don't like black, so I want to change that. So you can do it live in the meeting, for example. That is a unique capability. And this is one of the reasons why many people want to use the SimCenter Test Lab software. Okay, so that is one thing. Now, if we go back to the presentation, like I was saying, so for the Excel file, we need a certain header, but once we have that, data can be read in test lab. And then if there is an ASCII file, for example, an ASCII file can also be read, and we provide header in a certain format, required format. And once we do that, then the data can be read and accessed and plotted in test lab and then used for further analysis. Let's say this is time history data. If you want to do some frequency domain calculations, like calculating a spectrum or looking at tone to noise ratio and things like that, all that can be done with that data. As I said previously, we have this additional install that can be done on top of TestLab install, and that is called a SimCenter TestLab 3D driver. This driver allows more in-depth analysis for certain file formats. Something like, let's say, like the Abacus file, like the ODB file format, or Nastran OP2 file, or Nastran Punch file. So you have that information, and there are several things that are supported from this. And even something like waterfalls are supported in the Punch file if they have certain annotation in it. Even the ANSYS RST files, they are read in there. When we install the SimCenter 3D driver, there are certain things we can do with what is called as the point mapping file and then the units file. So if we take the case of the Nastran OP2 or Nastran Punch file, in the file itself, there is no information about the unit system that it uses. It just has values. But if you know the unit system that was used for that analysis result, then you can specify that in that FE default units file. And you can say, hey, when we see pressure, treat it as Pascal. Or you can say, if you ran the analysis as megapascal, you can say just megapascal here. And acceleration, treat it as meter per second square or millimeter per second square. So you can specify what is the unit system you want to use to associate with the data that you have from the simulation. So for different quantities, you can specify the default units for it to be treated as. And the other thing is the point mapping. So as we saw in the Punch file, like when we open a Punch file, it will have node numbers just as a number, which we can relate to physically. So here we have a number, and we can say, if this is what you see in that, treat it as this here. So we can say that when we see this number, treat it as this node, subframe front left, :1. And when you see something like this number here, then treat it as microphone at center, or this number will be microphone at front left here. So we can specify this mapping file. And so when we browse to the data in TestLab, it will see this, and then based on that, it will transform it to something like this. So if it had 2510, and then it actually changed it to subframe 2510 based on the point mapping that we had included. Now notice here that when I browse to the TestLab data, I'm seeing a lot more information than what shows by default. And that comes from the fact that we have this thing called the relabeling.ini file, which you can put in your user configuration folder, and it will show that for the Nastran Punch file, we can take a look at information like the function class, which in this case is FRF, and then the point ID, point direction, reference point ID, reference point direction, and such. So all that information can be shown just by browsing to that data without having to convert to any other file format. So that's what makes this such a great relationship, because one, TestLab is very flexible with what it wants, how it can handle different types of data. And then once the data is brought in, the CAE data can be analyzed in multiple ways. And that's why CAE data wants to come to TestLab. So that's why it makes such a great relationship between TestLab and CAE data. As we had said at the beginning, this particular webinar is part of the virtual prototype assembly series. And so let me give a brief overview or put a context on how this all works together, I guess. We are living in this fast-paced world in which everybody wants very quick results, with development cycles time reducing, and or the OEMs, they look at a lot of different variants and they want a quick analysis. And that comes in the context of electrification as well, where there are a lot of different things at play. Let's say the EDU, somebody wants to remove the ICE engine and put it with the electrical drive unit or a motor, how the whole characteristics change. And they want to analyze in such a way that they can make good quantitative NVH predictions based on either test data or simulation data. So traditionally, we have been looking at, for each variant, we would do the prototype testing. Once we have the physical prototype, let's say in the context of a vehicle, like automotive example, we'll wait for that. But that is no longer an option because there are so many variants and the development cycles, their time is reducing. And the other part of this is that there are a lot of different operating conditions, and then the usage of the control software in the context of electrification, that has increased tremendously. So how to take all these things into consideration to perform NVH prediction analysis? And that is where this virtual prototype assembly can be very helpful. So the virtual prototype assembly, you can think it of as a new tool that is available at your disposal that you can use for doing what if type of analysis in a meaningful way and in an easy way. In virtual prototype assembly, we characterize sources and receivers independently. Actually, no physical prototype is actually needed. The active component is characterized by invariant loads, or what are called as blocked forces. So blocked forces are the forces that characterize the strength of the load from the source, independent of what it is connected to. So if you take the context of an engine which is mounted to a subframe, there is the forces going from the engine to the subframe, and those are called the contact forces. And the force going in will depend on the connection between the engine and the subframe. What these blocked forces are, those are the forces generated by the engine independent of the connection it is associated with. So it's a characteristic of the source strength. So there can be different sources, and they can be structural sources or acoustic sources. And they can be like the electric drive unit, the transmission, electric power steering. All these are different types of sources, and they go through these passive components through mounts or connections and through subframe and suspension and body. And all these influence the NVH performance of the entire system. In this case, we are showing like an automotive example, but it easily applies to other contexts also, let's say like home appliances, like washing machines or dryers, or even in the aviation industry, or for that matter, even in ship industry and such. So we have these sources, these passive components, and the software controls associated with the use conditions of the equipment if you are interested in. Then all these three contribute to the complete NVH performance. And this virtual prototype assembly gives you a way to look at all the information, take these different factors into consideration, perform NVH analysis, and then produce meaningful results that can be viewed in an easy and intuitive way. Now, the various information that is needed for doing this type of analysis that can come from these active components, they can come from physical testing or from simulation, like SimCenter 3D simulation, for example. And similarly, these passive components, there are certain FRFs between the input and the output for each of these passive components. We need those FRFs, and they again come from test and CAE. So to further emphasize this point of this virtual prototype assembly, let's take an example of an electric drive unit. So if we take the situation of an electric drive unit, which you want to mount it on a subframe or an axle carrier at these two mounting points, and this subframe is attached to the vehicle body at these 4 attachment points, like these blue circles here. And there are some receiver locations here, which are inside the vehicle, like the microphones inside the cabin. So we want to see how, let's say, for example, if I want to change one electric drive unit to the other, how the interior noise is changing based on those changes. Or if you want to change the bushing rate, how does the whole thing affect it? So this problem can be broken down in this form of a block diagram, like A, B, and C. So this is the EDU, this is the subframe, and this is the vehicle body. They are connected through these mounts or bushings. And we have seen the way formulation for, if we are looking at the microphone sound pressure at this location, number 6, we can take the blocked forces generated by the source, which in this case is the EDU, and then go through this mathematical formulation, taking into consideration the bushing rate and the transfer functions in the subframe, and then finally be able to predict what this sound pressure is going to be. There is some complex math involved here, but that is where, because there is a process of inversion involved, that you want to collect good quality FRF data. But using the virtual prototype assembly, this whole thing can be represented in the form of what are called as components. So again, this whole thing, we have the EDU, the subframe, and the vehicle. There are different components connecting to it, and these components can be like an active component, which will have certain loads, or it will have certain FRFs like input and output to it. And there can be like connectors, that is a component represented by C, and we need dynamic stiffness for that. Or another component can be this PC, passive component, this subframe, and it needs FRFs between the input and output for the subframe. And the other thing is that there can be body receiver component. Again, this is FRS going from the body to the receiver location, which is the final target location. And that is also called the response point ID. Now here you may notice that in traditional TPA, we may be able to do from EDU mounted here and then from here directly to the receiver point. That is what we would have looked at in the classical TPA. But in VPA, that is virtual prototype assembly, we use component-based TPA, which includes the concept of multi-level substructuring. So we go from EDU to subframe input and subframe, from the subframe output to the body, and then from the body to the final receiver location. So this is the context of VPA, and we can see how we can build the model very simply in this form here. We need to put in a lot of data into this, and so that data can come from test or from simulation. So one of the things is that test scenario, like what is the operating conditions over which you want this model to generate this results, and that can be in the form of speed sweeps or RPM sweeps. And this information can come from our sister product called SimCenter AMISIM 1D simulation. So that can provide the input. Let's take a look at this virtual prototype assembly and see how we can build a component from test data, which let's see how easily it can be done. So here I have some data from this, and then I go to this test data that I have, and I'm going to look at certain number of FRFs, and this is test data. First, I want to show you the process in how to do it in test data. Then we'll see how this is done with CAE data. So I have these FRFs between EDU to body. So I'm going to put these FRFs into the input basket. Then I go to this VPA definition. So this is an add-in which requires like 15 tokens. And I can say this is a passive component, and this formulation is based on block forces. Then I can replace the data here. I'll be able to see a body and all the FRF points that are available. So this is a passive component, so it needs the inputs and then the outputs. So inputs in this case is the EDU, and the output is on the body side, right? So I'm going to select that. So then here we have only the translational degrees of freedom, not the rotational degrees. And then it shows like finds the matrix of what are the different points here. And we can look at the data, and we can also look at all the data, like all the full matrix of this 24 by 24 matrix, and look at the data in the form of this FRAC called frequency response assurance criterion. And that tells us how well the reciprocal FRFs are matching with each other. Let me change this color scale to inverse so that red will mean bad and blue will mean good. And so blue color means along the diagonal, it will always be 1 because that is like the driving point FRF. But off diagonal elements, we want them to be as close to 1. They're not always that high, but they're decent. And so here we have this test data, and then I can publish this data and then give it this name. I want to call it subframe underscore test underscore demo 1. I can create this, and then I say publish. Then it is published, and then we go to this VPA assembler, this add-in, and in this add-in, now I can create a passive component using that subframe test demo that I just created. So you can see how easy it is. We can just bring it here. Now I want to show that the same thing can be done with the CAE data also. Similarly, we can generate the same type of FRFs from our tool called SimCenter 3D. SimCenter 3D is an analysis software like which can take the FE model and do some analysis and generate the results for FRFs, for example. In this example, we'll have a subframe model, and for the subframe, there are certain inputs and output locations. And the inputs shown by this number 3, those are the engine mount, control arm left and control arm right. And then the subframe 4 locations, those are the output locations. And we are considering like 6 degrees of freedom for each input and output. So in this scenario, we want to do some analysis and show how SimCenter 3D can generate these FRFs using this solver 1111. Shall I initiate that video for showing how this analysis can be done in SimCenter 3D? Okay, I'm going to play it and it will mute myself. There is some voice also recorded with it, so please listen.
Welcome to this video of how to create DFRFs on SimCenter 3D and importing them to SimCenter TestLab. As a first step, you should open the mesh file of your component. Before we start the simulation, we need to create some input points and output points, and to do so, we will use 1D connections. For every input and output point, we'll select a center point of the specific connection and connect them to the respective face. We'll repeat these steps for all the connections using an RBE3 element. This subframe contains 3 inputs, the 2 lower control arms, and 1 from an engine mount, and 4 outputs, which are the connections between the subframe and the body. The 1D connection process starts from selecting a point, in this case the center point between the center of the circumferences and the respective inner face. The same will be applied for the inputs. Great, once the mesh is done and the connections or the RBE3 elements are done, we can display the number of nodes for better identification. In total, we'll be selecting 7 points. Now we can start the simulation by creating a new simulation file, giving it a name, and selecting the solution 111 Modal Frequency Response Functions. After, we should create unit loads at the input and output locations. For every input, we'll cite the 6 degrees of freedom, the 3 translational forces, and the 3 momentums. Then, it's necessary to indicate which outputs of the simulation we are interested in. In this case, we'll select the acceleration output for the 7 input and output points. Okay, once these parameters are defined, we need to specify a new forcing frequency that will be applied. In this case, we will select linear sweep from 10 Hz to 1000 Hz with a step value of 1 Hz. We apply this force frequency to the list, and also we define a structural damping of our structure. Once this is done, we can start to solve our simulation. The solution will take some minutes. Once the solution is done, we can check the results. Under the results, we can select post-process scenario. On the post-process scenario of SimCenter 3D, we can then create and visualize the FRFs. We can filter by node name and also for the directions.
So we saw in SimCenter 3D how to generate the FRFs using this Solver 111. Once that is done, the next step is to use that data from that simulation, and it was in the form of an OP2 file result that was generated. And that file, I can browse to it, and this is the result file that was generated, and I'm able to look at it in TestLab. And we use this point mapping to name the points using this convention, right? So for each of the node numbers that they had, like we mapped it to a corresponding point that we can fully relate. And I'm going to put this in the input basket. Then I go to this VPA definition tab, and I will say, hey, this is a passive component, and I'm going to replace the data. So basically, I'm following the steps similar to what I did previously with the test data. These are the input points, these subframes, these are the response points. And here in this case, we have translational as well as rotational degrees of freedom. And all this data can be viewed quickly in this software. So if I go back here and show you this, so in this context, we have this B, 3, and 4, and these are the 3 inputs and 4 outputs, and then each has 6 degrees of freedom. And what we need that information is to do the full TPA. We have this between 3 and 4. We need this matrix of points between 3 and 4, and FRFs corresponding to the 4, 4, like input and output at the same locations, and at the 3, 3. All this information is shown in this table if we have it. And if you want to look at them, we have that, just like the way we did previously with the test data. Now, once the data is here, I can publish it, and I can say this is subframe underscore CAE underscore demo2. And I say publish, then it will take all this data and put it into this component library. And that library can be stored locally. And in fact, it can also be stored in a centralized way so that once you publish it, maybe other people like some design engineers or performance engineers, they can access to it. And then when we go to the VPA assembler, remember that subframe test demo one that we had created. Now we are going to create another one for the CAE, and I can similarly bring it in. So the same process that we followed for the test, we can follow for the CAE, and we can use it seamlessly. We can integrate the information from different sources so that we can process and then analyze the data in a quick and efficient way. And it is very intuitive. So I showed you the example of this structural vibration kind of data, but then if I have some acoustic type of data, like transfer functions between body and receiver, let's say, so that will mean, so going from 2 to 6 from the EDU to the vehicle body. I have a set of FRS for that, so we can take a look at that, and I'm going to put that in here also. So I have this. This is acoustic FRFs. So output is pressure, input is volume acceleration. So I can select all these. Select all the FRFs, and I say replace an input basket. Actually, I could have right-clicked here and then put that also input basket. Doesn't matter. And then I will say this is a body receiver point, and I can say direct loads, and I say replace. And for this one, we have the input coming from the EDU, and the output, the final target is from microphones. EDU is the input. Now I have the full matrix here of all the FRFs I can plot here. Then I can hit publish, and then I can say this is body underscore CAE underscore CAE. Let's say if I just say that and I hit enter and I say publish, then I can use this information again in the VPA assembler. Notice here, this is P over Q, pressure over volume acceleration. So that has pressure over meter cube per second square unit. And when I go to this body receiver, I have this body underscore CAE. I can then put that, and if I want, I can connect to it as well. While I showed you the case for FRF, similarly, we can bring in acoustic loads or structural loads. All that can be categorized in a similar way. We can see that seamlessly we can bring in CAE data into test lab and use this in this VPA model together. Like both of them can collaborate to give us high quality results. So with that, I want to say there's some final thoughts that we saw that there are several different types of file format that can be easily brought into test lab and can be used for analysis. And then we got an overview of VPA, which is a powerful tool for NVH performance prediction for a fully assembled dynamic system. The bringing in of the simulation data into test lab, that has another added benefit, and that is the collaboration between OEMs and suppliers. Many times suppliers, they don't want to give the full 3D model of their system because due to confidentiality reasons. But if you want like a subset of the data, let's say that if you request for only the block forces, maybe they will give that information, and then we can incorporate that into the full vehicle body model, for example, and then do the prediction from there. So this VPA is a way of thinking of better collaboration between OEMs and suppliers as well, in addition to the hybrid between test and CAE. That brings us to the conclusion of this webinar. I'm more than happy to answer any questions you may have. Thank you very much for your time. Really appreciate it. And we look forward to your participation in the next webinars also.